In this video, we'll introduce what are inflection points or points of inflection. An inflection point is a point where a curve goes from concave upward to concave downward, or from concave downward to concave upward. So for example, we have three graphs of inflection points. The first point, you can tell before this point you have concave downward, and then after this point you have concave upward. Similar here, upward first, and then after the inflection point, concave downward, and similar for the third one. We know when a graph is concave upward, the second derivative of f of x is positive, and when it's concave downward, the second derivative of f of x is negative. So at the inflection point, the second derivative of f of x is equal to 0 or does not exist. Let's look at one example here. We're given the function f of x equals the natural log of x squared plus 4, and we want to find the inflection points or inflection point. That means we need to find when the second derivative of f of x is equal to 0 or does not exist. Okay, so let's start with the second derivative of f of x. Well, we'll start with the first derivative of f of x. So taking the first derivative of f of x, we have 1 over x squared plus 4. Then take the derivative of x squared plus 4, that is 2x. All right, so it is 2x over x squared plus 4. First derivative. Now take the second derivative. Take the derivative of the first derivative. So obviously this is a quotient. We'll use the quotient rule. So that is 2 times x squared plus 4 minus 2x times 2x divided by x squared plus 4 squared. Okay, simplify this a little bit. We have 2x squared plus 8 minus 4x squared over x squared plus 4 squared, which is negative 2x squared plus 8 divided by x squared plus 4 squared. First of all, I would like to check if at any place this expression is undefined. Well, this expression is undefined if and only if the bottom is equal to 0, but the bottom will never equal to 0 because the bottom is always greater than or equal to 16, right? So we don't have this case. But let's just look at the second derivative equal to 0 case. So we'll make the second derivative equal to 0. So that is negative 2x squared plus 8 over x squared plus 4 squared equal to 0. This expression is equal to 0 if and only if the top is equal to 0. So this problem becomes negative 2x squared plus 8 is equal to 0. So x squared equals 4. We have two solutions. One is 2, one is negative 2. So the inflection points, we have two inflection points. One start with 2, one start with negative 2. Right? To find what those 2 points are, we need to plug in 2 and negative 2 into your f of x. So f of 2 goes here, right? So to do a little bit of calculation, that's ln of 8. And f of negative 2 goes here, which is also ln of 8. Right, so we have two inflection points. 2 ln of 8 and negative 2 ln of 8. So how does it work? Well, the two inflection points, one is negative 2, one starts with 2, and these two numbers cutting the whole number line into 3 intervals, 2 to infinity. We'll pick a test point from each interval. Right. Here I pick negative 3, here put 0, here 3, and we'll put the test point into the second derivative of f of x. And if each number is making the second derivative positive, then the whole interval is concave upward, and if the second derivative is negative during that interval, then the whole interval is concave downward. So let's check. If you plug in negative 3 into a second derivative of f of x, you have negative over here, positive here, and negative again over here. So your graph will look like something like this: concave down, concave up, and then concave down, right? So for these two intervals, your graph will be concave downward, and in the interval of negative 2 and to 2, your graph will concave upward. So your graph is kind of like something like this, right? Not just a sketch. So where the negative 2 and at 2 you have inflection points. So the graph changed from concave downward to concave upward, and then at the 2 change from concave upward to concave downward. Now let's look at this problem. We're given a f of x. We want to find the relative maximum and maximum minimum inflection points and sketch the graph. We'll start with local maximum or minimum. To find that, we want to find when the critical points, right? So that's the first derivative of x, when is equal to 0 or does not exist. So let's start with the first derivative of f of x. That will give you, okay, so we can see this as a quotient. So quotient rule, that will be 1, right? Derivative of x times x squared plus 9 minus x times 2x divided by x squared plus 9 squared. So simplify this a little bit. It looks like it's negative x squared plus 9 over x squared plus 9 squared. We can factor it to make it a little bit easier for later. That's negative x plus 3 times x minus 3 over x squared plus 9 squared. Okay, the bottom will always be positive. So we don't have the case that the derivative of f of x doesn't exist. So let's just look at when is equal to 0. So that is the derivative of f of x equal to 0. Excuse me, it's this expression equal to 0. Okay, this expression is equal to 0 if and only if the top is 0. The top is 0, which is this part. Or you can't add the negative sign, doesn't matter over here. The top is 0 if and only if x is equal to negative 3 or x is equal to 3. So we have two critical values. One is negative 3, one is 3. And now I'm going to find the corresponding critical points, which is to find negative 3 f of negative 3, which is negative 1/6. I skipped the steps over here. And 3, f of 3 is 1/6. These 2 points are candidates for the local maximum and local minimum. How do we decide if they're local maximum or local minimum? We can use the second derivative to decide. So I will take the second derivative of f of x, which is, I'll use this part. So take the derivative of this expression, which is the first derivative of f of x. So again, chain rule, quotient rule. So that will give you, take the derivative of the top, that's negative 2x, times the bottom squared, okay, minus the top times the derivative of the bottom. So that will be chain rule. So that is, where is it? Okay, there it is. So first of all, it's 2 times x squared plus 9, then times the derivative of x squared plus 9, which is 2x, now divided by x squared plus 9 squared, which is to the 4th power. Now let's simplify this a little bit. And to simplify this, you'll get 2x times x squared minus 27 divided by x squared plus 9 to the 3rd power. So we'll use the second derivative to decide if these 2 critical points are local maximum or local minimum. So that means we'll find the second derivative of f of negative 3 first. That will give us, I just want to decide is positive or negative. So negative times negative divided by positive. Overall it's positive, and so that means it's concave up on negative 3, negative 1/6, right? So this point is concave up, and that now let's calculate the second derivative of f of 3. That's positive times negative divided by positive, which is negative. So that's concave down at this point, right? So that means negative 3, negative 1/6. This is a local minimum, and whereas 3, 1/6, this is a local maximum. But local, because it's not absolute maximum. This means our graph will decrease, right, from negative infinity to negative 3, and increase from negative 3 to 3, and decrease again from 3 to infinity. Right? That solves part A. Now let's look at part B, the inflection points. So to find the inflection points, we need to know when the second derivative of f of x is equal to 0 or does not exist. Okay, so we'll look at this expression, right? First of all, the bottom is always greater than 0, so we don't have the case where the bottom is equal to 0, so at no point, no x, will this expression be undefined. So, okay, it will never, does not exist. So we'll look at when the second derivative of f of x is equal to 0. So we'll make 2x times x squared minus 27 over x squared plus 9 cubed equal to 0. This expression is equal to 0 as long as the top is equal to 0, right? So that's 2x times x squared minus 27 is equal to 0. Here you can factor it as, if you want to factor this, that's x, you see this as 3, well, square root of 27 squared, right? So that's 3 square root of 3 times x minus 3 square root of 3 equals 0. Now we have 3 solutions. One is 0, one is negative 3 square root of 3, one is positive 3 square root of 3. Okay, so 3 inflection points. Now, we'll put these 3 points on the graph, which is on the number line, right? Starting from the smallest, negative 3 square root of 3, then the middle one 0, then the greatest is 3 square root of 3. Okay, now, these 3 points are cutting our number line into 4 intervals. Negative 3 square root of 3 to 0, then from 0 to 3 square root of 3, and the last one is 3 square root of 3 to infinity. Okay, 4 intervals. We'll pick a test point in each interval. Let's say over here something less than negative square root of 27. Let's pick 6. That's square root of 36. Right here, I'll put negative 1. Here, put 1. Here, I put positive 6, or test point. Test points. Okay, now we will test if these numbers will make the second derivative of f of x positive or negative, just to check the signs. Okay, so to plug in negative 6 into the second derivative, which is over here, that is negative times positive divided by positive. So overall it's negative, right? Plug in 1, that's negative 1, negative times negative divided by positive. So overall it's positive, right? And plug in 1, positive times negative. So overall it's negative. Plug in 6, that will be positive times positive. So overall positive. All right. So this means during this interval, during the first and the third interval, you will have your graph will be concave downward, right? Because the second derivative of x is negative, and on the second and the fourth interval, it will concave upward. Oh, I haven't found the inflection points yet. The inflection points is negative 3 square root of 3 and f of negative 3 square root of 3. I'll do that calculation later. And then 0, f of 0, whatever that is, and 3 square root of 3, f square 3 square root of 3. So complete the calculation. That will be plug into the original f of x, plug into here. That will be negative square root of 3 over 12. I did it on the scratch paper. 0 here, and that's square root of 3 over 12. And these 3 are the inflection points. Now let's scratch the graph. I marked the 2 critical points here as our green 2 points, and the 3 red dots are our inflection points. Okay, and we know for the first green point is the local minimum, and the second is the local maximum, and our graph roughly look like this. So this is where this at this point is concave. First is concave down here, right? And then somehow it's concave up. Excuse me, this is the local minimum, so it's like this, and then concave up at this interval, and then go to the local maximum, then concave down again, passing this point, but it's concave down here. Okay, sorry about my graph. Looks like there's another, so it should be like it's concave down here, so kind of like this, and over here it's concave up without having another local minimum, so it's kind of okay, this is how the graph will look like roughly.